Physical science.
Physical science time, I guess again we could say physical science time again. We're going to talk now about Newton's second law. Is that what I mean? I don't mean that. Forgive me. We already talked about Newton's second law in this class. We're going to talk about projectile motion, circular motion. Well, there's one other thing here. And gravity. Oh yeah, gravity.
Oh, that thing.
I should put a and or say. This little symbol, the ampersand, you know about the ampersand.
Nope.
This is an ampersand. You've seen it at least, even if you don't know about it. The ampersand is called that because it used to be part of the alphabet. I think probably in the late 17 and early 1800s. They would say it W, X, Y, and Z, and per se and, which means and all by itself. So this was and all by itself. And so eventually that got corrupted to be ampersand. And per se and became ampersand. Anyway, that symbol just means and. It comes from the symbol, the Latin and French words for and is et. And so this, fancier than I did it, but that eventually became this symbol. Kind of cool.
Not very physical science of you, Mr.
Mr. Kyle.
That would be et, which is and. Anyway, not very physical science, but it is important to know about things other than physical science.
Yes.
I wouldn't. All I know about is this and tigers. Yes, Peyton.
Do you know any French folklore?
I know almost everything. Let's move on. Okay, so today we're going to talk about these things in the reverse order. Let's talk about gravity first. Gravity. Okay.
Great.
I'm going to have you fill in the blanks here. Gravity, and think about this before you just answer. You guys are really in the habit of just shouting out answers that you think have a 1% chance of being right. But why don't you just stew on it for a second and then get an answer that has a 2% chance of being right. Gravity depends on something
Mass.
and
Cyrus.
and something else. I'm not going to say that's wrong, guys. In fact, it's right. It's not quite all the way right, though. But gravity depends on something, and it depends on something else.
Wait.
Well, actually, the force of gravity, if you remember, is the weight of an object.
Yeah.
The force of gravity acting on you is your weight. So it's not that, but very good guess.
Mass and Earth.
But it's not just one mass. It's
All mass.
Oh,
okay.
yeah.
Remember, everything in the universe attracts everything else. Depends on the masses of both objects. We talk about the force of gravity acting between two objects always. Gravity technically is pulling you in literally every single direction. Every particle in the universe attracts every other particle in the universe gravitationally. However, the gravity that you notice, and because of the second thing, the gravity that you notice is pulling you all one direction, which is which way? Down. Yeah, pulling you down. But anyway, gravity depends on the masses of two objects, of each object, and what else? So this is true, which it is. How come you're not more attracted to the sun than you are to planet Sun?
Distance.
Yes, and the distance between them. Actually, it's the inverse square of the distance between them.
Oh, come on.
The inverse square of the distance between them. So if the masses get bigger, what must happen to the force of gravity between them? It gets bigger too. What has a bigger gravitational attraction?
Well,
The Earth and the school building, or the Earth and this marker?
The Earth and the school building.
Because it depends on both masses. So in those two examples, the mass of the Earth is the same. So that we don't worry about that. But the mass of the school is much bigger than the mass of the marker, and so the mass of the school is more attracted to the mass of Earth because it has itself more mass. The inverse square. So first of all, what is it? When we talk about squares in mathematics, what does that mean?
it's like
So if I have some quantity x and I square it, what does that mean?
you multiply x by itself.
Yeah, I multiply x by x, which we usually write as x to the second power, right? X squared. So what would the inverse square be?
Negative.
No, that would be opposite square. What would the inverse square be?
X divided by
What divided by
x divided by x.
It's 1 divided by x squared. So inverse just means it's on the bottom of the fraction. It's in the denominator instead of the numerator. It depends on the inverse square of the distance. So the further away these two objects get, what happens to the the strength of gravity between them?
It's
It gets weaker. So it's gravity and mass are what kind of proportional?
Inversely.
Directly proportional. Gravity and distance are inversely proportional, but not just inversely, but are proportional to the inverse square. Proportional to the inverse square. Meaning that the farther away you get, not only does it get weaker, but for instance, if you're 3 times as far away, how much weaker would gravity be?
3 times.
No. No? 3 times farther away, because it's the inverse square, gravity would be,
1/3.
no? Not 1/3, but the inverse square, so what's the square of 3?
1.5.
1/9.
1/9. It would be 1/9. If you were 5 times further away, gravity would be 1/25. If you were 10 times further away, gravity would be 1/100. So instead of dropping off like this on a graph, it drops off like this. A curve.
So it's a really big
An
curve.
exponential decay, we say. Exponential decay. In fact, this is a primary example of exponential decay. We can write this as an equation. Let's write this down. F sub g. What's another way of writing F sub g? W. Yeah. Weight. F sub g equals capital G times the quantity m1, m2 over r squared. Write this down, please. Where F sub g or W, F sub g or W is what?
Force of gravity.
Yep, force of gravity, or
Sorry, no.
well, what else would we call it? Force of gravity or
Wait.
weight, measured in probably.
Pound.
Mm,
Kilograms.
no, for the people who do science, it's measured in newtons. Yeah, force of gravity measured in newtons. Capital G is what we call the universal gravitational constant. And this one we can write down not just the unit, which we will, but we can also write down the exact value because it's a constant. Colin, you have a question?
No, can I get a new notebook?
Not right this second. Thank you for asking. I will get you one after a while. The universal gravitational constant, write this exact value down. 6.67 times 10 to the negative 11th. You know about scientific notation, right?
Yeah.
Does anyone not know about scientific notation? Okay, good. 6.67 times 10 to the negative 11th, and it's measured in Newton meters squared per kilogram squared. So in this case, since it's a constant, we know not just the unit.
What did you write down?
6.67 times 10 to the negative 11 Newton meters squared per kilogram squared.
That is a large number.
It is an extremely small number.
Well, large in the sense that it is very long number.
It isn't. It takes up a lot of room on your page,
A lot.
but it's a very, very small number. This is 0 point and then 10 zeros, 6, 7.
Still pretty.
Very, 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 very small.
Still pretty large number.
M1 and M2 are what? Probably masses measured in. No. What do we measure mass in?
Kilograms.
Kilograms. Thank you. And then R is, it's abbreviated R because it means radius, but I'm just going to call it distance. We can also use the lowercase letter d. Distance. What do we measure distance in? Hey, buddy.
Meters.
Is that in
Meters. 10 to the negative 11. Yes. This is given. We know this because I just wrote it down for you. It's always this number. It's always this number. Okay, you're good with that?
Yes.
Almost.
This capital G is always this number. Okay? So far, so good.
One sec. Your hand down.
Capital G is always this number. So could we substitute for capital G?
No.
Yeah, we can. 'Cause it's always this number. We know what the capital G is. We know what it's always going to be. If we know the mass of me, for instance, we could put that in for M1. Can we know the mass of Earth?
Yeah.
Sure, yeah. Where would you find the mass of Earth?
In your book.
Possibly. It might be in there. I know it's in the physics book. the Google. You could type in what is the mass of Earth, and you could go to www.yahoo.com, type in Google, click on the link, and then go to what is the mass of Earth.com, and that would tell you the mass of Earth. So I could substitute in my mass, which we could figure out. This is how we figure out Dwayne the Rock Johnson's. I weigh 440 pounds too, so it's the same thing. Pure muscle also. This we could substitute in the mass of Earth from Google. This, how far am I from Earth? Be very careful though.
Not very right on.
You should know that when we do this, here's me, here's Earth. When we do this, it's always from the center of mass of one to the center of mass of the other. So write this down. Someone should be writing this down. It's always from the center of mass of one thing to the other. So that means that if I have the force of gravity between these two markers, when they're touching, what would the distance between them be if we didn't use this? If we didn't know this, what would the distance between them be? They're touching. What's the distance between them?
0.
0. Can we divide this by 0? No, that breaks the universe. But I can't get their center of masses together. In fact, if I could break them, and they would, but their center of masses would be different. I can't physically make them touch. So the center of mass to my center of mass, this ends up to be, if I remember correctly, roughly 2,400 meters. That could be totally wrong. But basically it's what? It ends up being, even with the height of the school in there, this is what part of Earth?
The core.
Yeah, that's why I pointed out the core. But this, what part of the circle is this? What I'm indicating here? This thing. Yeah, the radius. That's why I abbreviated R. The radius of planet Earth. So I could find, what would I be finding if I did that? I could type in, to my calculator, 6.67 times 10 to the negative 11 times 100 kilograms times the mass of Earth is something like 3 times 10 to the 25th kilograms, divided by, that number might be totally wrong, but 2,400 meters squared. What would I be getting?
The force of gravity.
The force of gravity, which is also my
On your
weight. So I'd just be finding my weight in newtons, which should be the same as if I use W equals mg. Why would we ever bother using this thing? First of all, what does it help us illustrate?
Mass.
Probably not more precise. That just means the number would have more decimal points. What does it help us know though? Unlike W equals mg or about F equals ma, this is how it works. This is what gravity actually depends on. We're plugging in the things that gravity actually depends on. Also, we might not be able to use W equals mg for something like the effect of gravity from the sun to Jupiter. So this is used very commonly for celestial bodies like planets and galaxies, and it's used for when I want to tell my students about how gravity is working, what gravity actually depends on. Because if we use F equals ma, that just means we just use the mass and the acceleration of gravity equal the weight. But that's not really what gravity is actually up to. This is. Questions about universal gravity. We call this universal. What does that mean? What's universal mean?
The big great galaxy.
Yeah, it's all everything. Literally everything in existence. Mass, energy, everything applies to this. In fact, we can calculate the force of gravity between this baby marker, color, poop brown, and Mars. We could calculate that very, very easily. We just look up the numbers. Okay, questions about that? No. We have just a little bit of time, so what I'm going to do is this. We're going to talk about projectile and circular motion together, which I always do, but we're going to do it kind of briefly, so I'm going to rely on you to read up on this. And there are videos from last year of my telling previous freshmen about this. You can watch that. There are videos of my telling physics students about that. You can watch that. Also, there are good YouTube videos you can watch about this, so you can watch those too. So now it's going to talk about projectile and circular motion. Okay, ready? What's projectile?
Projectile.
You have a question, Cole?
I ran out of space.
Give him a piece of paper for now. What's a projectile? When do you hear the word projectile?
Like if you throw something.
Throw. Yeah, projectile just means to have thrown. Projectile, thrown. Projectile motion, write this down, please. Projectile motion, for one thing, follows a parabolic path. In fact, that's how, when you look at the conic sections of has Mr. Silly talked to you about conic sections?
No.
Okay, well, he will eventually, but the conic sections, though, the definition of the parabola is the shape of an object's flight path.
Yeah.
So if I throw this marker, which I'm going to paint, ready? Woo! The shape it traveled in was woo, right? It's a parabola, roughly a parabola. Follows a parabolic path. And you need to know that it has separate actions in the x and oops, not Annie, and y axes. So if I graph this motion that I just did when I threw the marker to Peyton, where's the x-axis?
Bottom.
Yeah, it's the cross one. Where's the y-axis? I'm already doing it.
Vertical.
The y-axis. Okay. In the x-axis, it is equal to the object being rolled on a frictionless surface. In the y-axis, it's equal to what? Can you guess? If the object were so the x-axis in this way, it's going along as if it had just been rolled on the floor. That's the x-axis path. What's it doing in the y-axis? As if it had been
Height. Thrown up.
thrown straight up and then fallen straight back down. Straight up and straight down.
So what does it say after object and x-axis?
Being rolled on a frictionless surface. Let's imagine the poop brown marker is right here in this part of its path. Whee! What forces are acting on it in the x direction? What horizontal forces are acting on it? Be very careful. In the x direction. In this way, what forces are being acted on it?
Air resistance.
Air resistance, and that should be it. If we negate air resistance, which we usually do in this part of physics, at least at this level, what forces are acting on it? In the x direction. Yeah, but we're negating air resistance, so what? That's not in the x direction. So none. There are no forces acting on it in the x. No forces. If there are no forces acting on it in the x, is it accelerating in the x? Can it be accelerating in the x?
Yes.
No net force means no acceleration. So its motion is not changing in the x. It's just rolling as if it were in a straight line at a constant speed. What forces are acting on it in the y for the entire path? Gravity. Acting always. Well, when we throw it up, gravity acts up, right?
Yeah.
No, that's crazy. I was tricking you. Yeah, gravity's always acting down. That's why when we throw something straight up and then back down, as it's going up, what's it doing? It's slowing down because gravity's still acting down. And then as it's going down, it goes faster and faster because gravity's still acting down. So in the y-axis, only gravity is acting. So why does this path get curved? Well, at each little second that goes by, it should be slowing down, down in the x direction, right? Mm-hmm. And it is. In the y direction. In the x direction, it's just moving boop, 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 one increment the same exact way. So if I throw this in a straight line at Peyton, ready? Oh, sorry, Justin.
Targeted assault.
Anyway, if I can't throw it in a straight line because gravity's always acting on it. But if I try to throw it fast enough that it approximates a straight line, that it leveled out. Yeah, like a bullet. But here's the thing. This is what we're going to get to before we end. If I have a gun, I didn't bring it to school. If I have a gun,
That's a good gun.
if I have a gun,
I'm driving.
and I have a bullet that's the exact same as the bullet's going to come out of the gun, and I fire the bullet from the gun, and I drop this bullet at the same time, which one hits the ground first?
Bullet dropping.
Well, yeah, you're wrong, though. Actually, they both hit the exact same time. So even though this bullet has gone a much, much greater x distance, which it has, maybe even a mile, they both will hit the ground at the exact same time. At the
So when your
exact same
bullet hits
time.
the ground, so when
Give me the
the shell is
We gotta
flying,
talk about the velocity.
Give me. Yeah, you're wrong though, Colton, because the gun's only providing a force for a second. It's only providing velocity in what direction?
straight.
Yeah, the x direction. So it's going extremely quickly, but just in the x. The muzzle velocity of the gun is all this way, unless you're shooting it down, which you're probably not. The y velocity is entirely determined by what? Only by
Gravity.
gravity. The only thing acting here is gravity,
And
just
this-
like for this bullet.
And this is only if like you're aiming it straight and not.
Yeah, obviously not. If you have it angled up, then that's going up in the air for a while. But these are bullets. Yeah, I'm gonna drop one and shoot one out of a gun. Ready?
Almost.
Well, they almost the same.
They are the same. It's hard to see on the camera, and it's hard to see because these have so much. Where's my other deal de los muertos school? That's what I usually use. Anyway, do you have questions about the circular motion as part of this? Because any motion in a curve. No, don't go yet. Write this one last thing down. Any motion in a curved path is circular motion.
Any motion in a curved path is circular motion.
Yeah, it doesn't have to be a whole circle for it to be circular motion. And this counts as circular motion. There's more stuff to read about this in your book, and you need to do that. Do you have questions about what we covered today, though?
Yeah, no.
Well, what is your question, Cyrus? We'll talk more about this tomorrow when we do the. I can't do this.
That can.
Ah!
I've seen you.
Oh, you meant to say